Hi, this is Mr. Stansbury. I'm going to take you through some notes on section 1B, which is number sets. So let's get started. 1B, number sets. Okay, there's 1, 2, 3, 4, 5, 6, 7 of these that we're going to take a look at. So first one is n with a little star up here. And that stands for a set of numbers 1, 2, 3, 4, ... And this is called the set of all, and this is called counting numbers. Okay. Next one is n without the star, and that is 0, 1, 2, 3, 4, on and on to infinity, and this is called the set of all natural numbers. Alright. Next one is z, and I will always put a slash through my z so that it does not look like a 2. So z is a set of numbers which the book gives us 0, plus or minus 1, plus or minus 2, plus or minus 3. I like to think of it as set of all numbers ... negative 3, negative 2, negative 1, 0, 1, 2, 3, and this is the set of all, and these are integers. And again, stupid way to remember this, but it has always worked for me, is I think of this as integers with a z, and that's where the z comes in. So I think of that as integers. Take it or leave it. We have z plus is the next one, and that is 1, 2, 3, 4. Continued on is the set of all, and yep, you guessed it, positive integers. And you may be thinking, hey, wait a minute, we just did that. You're right, it's the same thing as the counting numbers. So these are the exact same thing. Alright, so counting numbers and integers, same thing. The next one we have is the with a little negative up there, and again, hopefully you have figured out that's negative 1, negative 2, negative 3, negative 4, and this is the set of all negative integers. All right, 2 more to go. These two are pretty big ones, though. Q is, and they have this written as P over Q, where P and Q are integers, and it's also important that you know that Q cannot equal 0. And if you think about that, why would they need to put that Q is not equal to 0? Because if you look at it up here, you know that one of your math rules that will make the math gods angry is trying to divide by 0. We know that we can't divide by 0, so that's why it has to be stated in here that Q cannot equal 0. So if you have that, let's see, this is the set of all, and this is called, sorry, these are called rational numbers. Okay, and again, the way I often remember that is I think of Q as quotient, and quotient is where you're dividing two numbers. So again, this is basically the rational numbers are any number that can be represented as a fraction. Okay, and then the last one is the big R, and again, you may sometimes see this as the big R with an extra line through it, kind of like the paragraph symbol. And basically, this is the set of all numbers that can be placed on the number line. And this is the set of all real numbers. Okay. So these are the big seven: counting numbers, natural numbers, integers, positive integers, negative integers, rational numbers, and real numbers. And again, this is any number that you could possibly think of, the real numbers. Alright, so next thing we are going to do is head off to take a look at some examples. Okay, so this is actually example 3 from page 20 in your book. Okay, and it says, show that A 0.45 and B, which is 0.135, are rational numbers. Alright, so again, if you'll remember from back before on our previous page here, we have rational numbers is something that can be represented as a fraction. So basically, if we can just take what we have here and show this as a fraction, then we're set, right? So that hopefully is pretty simple. For A, if it's 0.45, remember that you can actually say that as 45 hundredths. So just write it as 45 over 100. We've shown that that is a rational number. B, 100.135 can be read also as 135 thousandths. So that we have shown now that both of those are rational numbers because we express both of them as fractions. Alright, let's take a look at example 4, which is on page 21. Okay, these are a little bit more challenging, but that's good. We like a good challenge, right? Show that A, which is 0.777 repeating, B, which is 0.3636, also repeating, are rational numbers. Okay, not quite so easy, because this is, we can't say that that's 777 over 1,000, because again the 7s continue on. So I'm going to show you how the book does it, and then hopefully you can quickly catch on that there's a fairly nice shortcut on this. So let's take a look here. So here's A. We're just going to say let x equal 0.777, repeating. Okay. So we're going to multiply both sides by 10. So we get 10x equals, if you multiply this by 7, we just move the decimal over 1. So we get 7.777, repeating. Alright. We then rewrite this right side as 7 plus 0.777, repeating. And if you'll remember, 0.777 is x. So we can rewrite this as 10x equals 7 plus x, right? Subtract x from both sides, and we get 9x equals 7. So we would then divide both sides by 9 to get x by itself, and we get x equals 7/9. And that is, we've now shown that it's a rational number, because 0.7777 repeating is 7 divided by 9. And you can check it on your calculator and it works. We can do basically the same thing with B. So let x equal 0.3636, repeating. And on this one, since it's 2 digits instead of just the 1 digit that repeats, we're going to multiply by 100, so we can get 36.36 ... So multiply both sides by 100, and we get 100x equals 36.3636, repeating. And then just like what we did over here, we we rewrite this as 36 plus 0.3636. And again, remember that 0.3636 is just x, so we have that as 100x equals 36 plus x. We subtract x from both sides. We get 99x equals 36. Divide both sides by 99, and we get x equals 36 over 99. And we're done. Alright, now, hopefully you can look at that and say, hey, wait a minute, look, we got 0.777 and we put that over 9. We got 0.3636 and that ended up over 99. So basically, a shortcut way to do this that I have that we've figured out over the years here is just do this. However many digits are repeating, so there's only one digit that's repeating. 7 is the repeating digit, and you put it over 9 since there's just one repeating digit. Okay. On this one here, there's 2 repeating digits, so that would be 36 are the 2 repeating digits, and since there's 2, you put 2 9s underneath, so 36 over 99. Okay. Let me show you one more. Let's try another example. So let's just make our own. Let's say we have 0.412412 ... So shortcut way on this, since you certainly can do it this way, but the nice easy way to do that is we have 4, 1, and 2 are the 3 repeating numbers. So we do 4, 1, 2. Since there's 3 repeating numbers, we're going to have 3 9s on the bottom. That shows that this is a rational number. All right, hopefully that makes good sense. One last quick thing to talk about is irrational numbers. Let's see here. Irrational numbers can't be written as P over Q. It won't work. Okay. Some examples of irrational numbers, are square root of 2, square root of 3. Most square roots that aren't perfect squares, like square root of 4, wouldn't work because that's actually just 2. Other ones that a popular one that you might recognize would be pi. And basically, the reason why an irrational number can't be written as P over Q is none of these can be expressed as a fraction. They all have, let's write this down so we don't forget, irrational numbers have no end, meaning that they the number continues on forever and ever, and they do not repeat. Okay, so that's important to know about irrational numbers. They continue on forever and ever, and they do not repeat. Okay, a rational number can continue on forever and ever, but they have to repeat. Or it can it doesn't have to repeat, but it has to have like an ending, so it doesn't repeat, going on forever and ever. All right, so maybe let's just take a quick couple. Let's just take a look at a couple examples here. So example, again, we're just kind of making this up. This isn't in your book, but let's do this. Rational or irrational. Let's do A, and we have 7.31256, and then B is I don't know. Let's do square root of 71. Okay, so this one over here, again, it's a long decimal, but notice that it actually ends. Since it ends, that means that this is a rational number. And this one here, if you put square root of 71 into your calculator and you kept looking at the decimals, you'll notice that it goes on forever and it never repeats. So that means that this has to be irrational. Okay, so again, goes on forever and ever and doesn't repeat. And then rational either repeats or terminates, we call it, has an end spot. All right, hopefully this has been helpful. If you have any questions, feel free to ask me. All right,